All right, hi everyone. My name is Glenn Lockwood. I work in the Advanced Technologies Group at the National Energy Research Scientific Computing Center, otherwise known as NERSC, at the Lawrence Berkeley Lab. And I figure I'll talk about two things, what our storage looks like today, and more of what we're worried about storage looking like for tomorrow. So I know there's a lot of storage engineers in the room. So I'll start off with some speeds and feeds and just some high-level things, high-level comments about what we do. So at NERSC, we're the mission computing facility for the Department of Energy's Office of Science. So we provide computing resources for all DOE unclassified researchers. What this amounts to is last year in 2016, we had nearly 7,000 active users using our systems. That's spread over 750 unique science projects. And it's worth noting that about a third of those, or a little more than a third of those, involve experimental or observational data processing. So this is not necessarily people that are running giant simulations like in years past. We're serving an increasingly data-oriented user community. And then of these 750 projects, we've got over 650 unique applications. And our users are highly productive. Since we've got 7,000, we average about 2,000 refereed publications coming out year over year. And every decade or so, we get a Nobel Prize winner that has used our resources to do the work that won them their Nobel Prize. In terms of the speeds and feeds, so at NERSC, we're extremely diverse. We have a large user base, large amount of codes and applications and things that people want to do. But in terms of the storage that supports that, I'll talk about our file systems in a little more detail, but to give you a high-level overview, we do have two large supercomputing systems that produce the bulk of our I/O. That amounts to about 17,000 Lustre clients that are all mounting Lustre as direct native mounts. We process over 15,000 jobs per day, and at any given point during the year, we're running at over 90% utilization. And unlike other HPC centers in the DOE, we take all comers. So some of our jobs are extreme scale. They use large fractions of our system, but many of our jobs are using one node or even one core. And more of the data processing community is using these smaller levels of concurrency for their workflows. In terms of the actual storage architecture that we have at NERSC, right now we've got 4 tiers of storage. At the top is our burst buffer, which is attached to our Cori system, which is the green system shown at the bottom there. This is pretty new. We got it about 2 years ago, I want to say, and it went into full production after about a year and a half of early user and shaking out details of usability and performance. And that amounts to 1.8 petabytes of NVMe-based storage that's embedded directly within our Aries compute fabric. And we get about 1.6 terabytes per second on the average day out of that thing if we try. Underneath that is our Scratch file systems. We have a Scratch file system for each large-scale system that we have. Both of them are Lustre-based, so Edison has 3 actual namespaces, all based on Lustre, an aggregate of 168 gigabytes per second. And then Cori, which is our newer system, has 28 petabytes of Lustre, and that file system pushes about 700 gigabytes a second. So it's about half as fast at peak as our burst buffer. Below that, we have a project layer. So I'll have to respectfully disagree with yesterday's speakers, my colleagues from Lanolin, that they invented campaign storage. We've actually had project storage for many years, serving as sort of a global file system from which users can take the data from Scratch, which is not considered a resilient or durable data store. The data that they want to keep from that, they push down to the projects layer where they can keep it. And that is a much more durable storage. It's quoted, and it's backed up. It's snapshotted. And then below that is our archive. So we do have about 100 petabytes of tape with, I think, 2 petabytes of disk cache in front of that. And this follows the pretty typical storage hierarchy in terms of performance. As you go lower, the cost per gigabyte goes cheaper, but the performance goes down. And this is the layout as of today. In terms of what these data storage systems actually see on the average day, I just looked at my daily automated reports a couple days ago. And on our Cori Lustre-based file system, we had 900 terabytes of data written 3 days ago, and 1.8 petabytes of data read. So this right here tells us that, unlike many other HPC centers, our extreme scale storage is not just checkpoint and restart. We have a huge amount of read activity, which to me means we've got a lot of data going out, perhaps a lot of data analysis going on. And then in terms of our archive, we grow at a rate on this particular day of 181 terabytes going in. And surprisingly, there's a lot of data that comes out of our archive every day. So this day was actually pretty low in terms of the data that came out. On a typical day, and this is just very broad strokes here, our Lustre file systems have about a 50-50 read-write ratio. And our tape archive has a 60-40 write-to-read ratio. So most people talk about tape and they think it goes in and never comes out, and that's not entirely true for us. Mind you, the 60-40 write ratio is going into our archive system, which includes the disk cache. So we're not serving 40% of the data straight off of tape. And I think a large fraction of the data that is read actually is reread within the 30 days that it was written. So people are putting data in and then taking it right back out. So it is a pretty dynamic storage system that we have. And it's also fun to point out that on our tape archive system, we never throw out data ever, which means we've got data that goes back to about the beginning of NERSC. Some data is over 40 years old at this point. And we keep it around, and every once in a while someone does ask for it, and we give it to them. We have no idea if they can actually read it, but we do keep it for them. So that's what we have today. And my job in the Advanced Technologies group is to really not worry about today, but worry about what's coming tomorrow and figure out how we can get to tomorrow without really blowing our budget or making our users upset. So I wanted to, it seems like a lot of the really massive storage technology market is now being driven by hyperscale, as it should. I mean, the Googles and the Facebooks of the world store everyone's data, whereas we just store the data of 6,000 users. But unlike the hyperscalers and the technologies that they can deploy to satisfy their workload, at NERSC, we're not really a write once, read many shop. We do certainly have those workloads, but it is not the dominant form of data motion that we have. And like I said, we have a 50-50 read-write on our Lustre file system, 60-40 on our archive systems. So what that amounts to is shingled drives really haven't found a place in our data center yet. We're not entirely sure what role they'll play for us, but right now, the performance impacts are they don't match our workload. And unlike other HPC centers, we also don't have a pure checkpoint restart workload. So while burst buffers and similar flash-based technologies were originally envisioned to just absorb huge I/O bursts and then drain them out to the disk-based file system, that's not really how our burst buffer gets used on a day-to-day basis. There are certainly a lot of people that do checkpoint directly to it, but we also have a lot of use cases where people will bring data in that they want to analyze and leave it there for a few weeks and constantly run jobs against it as it lives on the flash. And then once they've done all the analysis they want, they just drop it and everything goes back to zero. Unlike the hyperscale and the enterprise world, our users are used to a batch-oriented workflow. So they submit a job, it sits in a queue for hopefully not too long, but it can be days. And then at some point later, they get their results back. And so this means they're a little more tolerant of high latency startup times. Whereas if you're open your Gmails and you want to read an email from 2 years ago, you don't want to wait for a tape to mount to get that email. It's a little bit more tolerable in our case, so that putting things on tape is really not an absolute showstopper for us. And as such, the dollars per gigabyte of tape is still pretty compelling to us. Tape is really cheap. It doesn't take up any power when it's not in use, and it lasts a really long time. So tape is not a technology that we're saying is dead and we're moving on from it. It still has a place in our data center, at least for the near-term future. And I would say that every day for us is like Black Friday for a place like Amazon. So on days when everyone is online shopping, you hear about these cases where elasticity needs to happen, and they get these unusual bursts of really high intensity I/O activity. And that's really our meat and potatoes. I did say that our workload is not entirely checkpoint restart, but when someone does checkpoint, it's they're pushing 400 gigabytes a second all at one time from every single compute node that we've got. or even a subset. So you can get 400 gigabytes a second from just a few hundred compute nodes if you really wanted to. So intense bursts are really what happen every day for us. But in addition to that, we also have a huge background workload of incoherent I/O that's happening from our smaller scale users. So on any given day, we'll see maybe 10 or 15 gigabytes per second of persistent read or write activity that's just happening nonstop for hours on end. And that's just from day-to-day traffic of people wanting to access their data for small-scale analysis to see what's going on. But because of these intense workloads and the amount of background traffic that's happening, in terms of our performance requirements, we kind of need it all. So we do need to have low latency because people want to be able to access their input decks really quickly and change something and kick off a job. But at the same time, they also need high bandwidth so that when they do read or write large files, they're not spending all of their precious wall clock time, which is the unit on which we charge our users, waiting for I/O to happen. And then many of our users like to generate lots of files. So scalable metadata is still pretty critical for us. And since we need all of these things, this is sort of what has driven us to this tiered model of storage, because there's not one single storage technology that can give us low latency, high bandwidth, and scalable metadata. And what this all really adds up to is that the solutions that are out there for enterprise and hyperscale, we could use them. And I think MarFS is a really good example, a proof of concept that you can take something like an object store and make it useful for users. But it's an imperfect fit. So the solutions that are out there being developed by Googles and Facebooks, they're not just drop-in for us. We do have to do a lot of legwork to even consider making them a viable option for our users and our workloads. So looking to the future in terms of performance, one of my pet peeves, or I like to get behind a podium and beat the drum about this, is that POSIX is, it's been around forever. It's what all of our applications are written to use for their I/O, but it's getting old, and it's really doing us a lot of harm in terms of continuing to scale. And a lot of people say this at conferences, but they don't often justify exactly why POSIX is so bad. So I figured I'd be a little bit more discriminating and say exactly what I think is bad and what's not so bad about POSIX. So really, when you look at POSIX and you say POSIX I/O is terrible, you really have to distinguish the POSIX I/O semantics from the POSIX I/O API. And the API is what everyone writes their applications against. They want to be able to open a file, read, write, close it, and have it work. The semantics are the stuff under the hood, like consistency, that guarantee that when you write some data to a file, that write will block until that data is persisted and someone else can come along and read it and see that version of the data that you just wrote. But there's a steep penalty to scalability when you enforce that level of consistency. So what we're starting to think about is what happens if you take the POSIX API, which is what everyone's applications use, but then rip out the semantics and replace them with something a little bit more scalable underneath, and then rely on the applications themselves to do what POSIX was strictly enforcing otherwise, in terms of making sure that there's no contention in terms of two different processes trying to write to the same part of the same file at the same time, which is actually not an unreasonable assumption, because as it turns out, in the past, you could not rely on POSIX consistency semantics to get good performance. You'd have lock contention, and you would just, it would work, but it would work terribly. So users have learned not to do that, and their applications actually don't rely on POSIX semantics as much as it is tempting to think they do. So, along this line, we can start thinking about trading POSIX for performance and letting users decide exactly what they do and don't need to let us break through the scalability barriers that our traditional file systems have been imposing. So just as an example, POSIX is a stateful I/O, so in order to write to a file, you must first open it. But as it turns out, having 17,000 processors open a single file takes a really long time. The scalability of open is pretty rough. But is there really a reason we need to open a file to write to it? I mean, the cloud people have solved this by just throwing out open and close and doing puts and gets against objects. So why can't we do that and just have open and close just be some kind of dummy thing that returns a file head or an object ID, and then have reads and writes against a file descriptor just translate to puts and gets? And then there's also the consistency question of, what is the price that we're paying to ensure that two overlapping writes to the same page produce consistent results? And this is just a plot showing that, for really small transactions, we pay a really steep latency penalty to enforce strong POSIX consistency. But the reality is, if you relax those and take out locking, or leave page caching in, but without locks, or a lot of file systems like PVFS just take out page cache entirely to avoid the consistency problem. Maybe an idea is to keep page cache, turn off locking, and just let users shoot themselves in the foot if they really want to. And the result of that is this orange line, which shows that if you just take away POSIX locking and give them page cache, you get really good latency for writes no matter what size your transactions are. So this was really just an overview of where we are and kind of where we're thinking. And I'd be interested in hearing what everyone else's thoughts are on the matter. Thank you.
Questions for Glenn? And I'd like to thank Glenn. We talked yesterday afternoon, and we were looking, Ellen and I have been looking for somebody from NERSC, and Glenn stepped up, so this is fantastic. Thank you. So questions?
Yeah, is this on? All right, great. So Glenn, I'm noticing like a theme here. So the guys at the lab, you guys all have a pretty unique workload that's different than the hyperscalers and the enterprise market, right? So you got hyperscale, enterprise, and then you guys, right? Mm-hmm. So your problem is very different. Your workloads are different. And the theme is everybody's talking about there's no system that really effectively does what you guys want it to. Is there any effort across the labs and the government-funded research community to develop something that does solve your problems? Because you're all saying the same thing.
So we're saying the same thing if you're standing far away from it, but the reality is that even within the labs, like NERSC, we've got 7,000 users. If you look at Argonne or Oak Ridge, which have much bigger systems than us, they've got hundreds of users. If you look at LANL, their workload is very mission specific. They've only got a couple applications they have to run that have very distinct I/O patterns. We've got hundreds of applications that we can't change.
Well, the POSIX use case, for instance, that's something we've all been talking about for years, like the limitations of POSIX, yet 90% of the workloads we use are all file-based. They hit Lustre, GPFS, Gluster, which usually, they require, the application itself requires POSIX or is written to assume that there's a POSIX-compliant file system sitting underneath it. So since we're all kind of getting hit with these penalties, I don't know, there's some basics we could all kind of work together to try to figure out to change because we're all being hit by the same limitation that the Googles have moved on to object storage to get away from, So I guess.
There's certainly room to work together. Are we recording this? I guess we are, so I have to be careful what I say.
Yeah,
that's correct.
Part of it is that, a lot of us are researchers, right? Yeah. And we all have different ideas of what the right answer is. And, it's hard to throw out your idea for someone else's better idea. Or maybe it's not a better idea, but it's easier to do, or it's just more tractable. The other part of it is, and it goes back to the panel yesterday, is that there actually have been efforts to extend POSIX and change POSIX in very slight ways or add new APIs to it to specifically help HPC workloads. And this happened in the late 2000s. Mm-hmm. And what that amounted to was that the POSIX people laughed us out of the room. And it was just, they were not interested in hearing what we had to say. And we had some of the best and brightest minds from the DOE labs coming together to put together a very simple set of extensions to POSIX, and it just didn't work. And maybe it's because the time wasn't right. So maybe it is time to revisit that. But that was a case where we did actually get together and come up with a good plan. It just wasn't the time.
Yeah. Well, so from my perspective in the industry, I mean, this is probably the most volatile time, and not from like a negative volatility perspective, but dynamic time in the storage industry. So we've got cloud migration, we've got the hyperscale guys that have come of age, we've got enterprise object storage platforms that are of age, reliable, not just for like some web application that the hyperscalers built. And we have the media transition to flash for like a lot of enterprise workloads, your scratch workloads, whatever, Mm-hmm. So now is a good time to begin having those conversations again, because I mean the capabilities are kind of completely different than they were 2 years ago. That doesn't happen often. So anyway, cool. Thanks, man.
Other questions? Go ahead.
So does the, excuse me, does the presence of the, can't you insert the required relaxation to POSIX at the burst buffer level rather than try and hack away at the parallel file system?
Yeah, so in fact, that's what we're doing. So our burst buffer has the option to mount with NFS style consistency. Users can opt in, and they do risk getting corruption if they don't write to 4K line pages. But part of the problem is that, although we have a 4-tier system, users can actually write directly to any tier. They could write straight from the compute nodes to tape if they really wanted to. And right now, the burst buffer is just not what people use by default because Lustre performance is not that bad. So they don't have a big enough carrot to wholesale go into the burst buffer and let us mess with their I/O and their I/O semantics for them. So really, most of the I/O goes against Lustre. So we would have to really get in at the Lustre level in order to start monkeying around with that.
So a quick question for Glenn. So are you saying, so if I understood you correctly, you're saying that POSIX is incremental changes to POSIX are okay, and it's more about the semantics? Is it? And so you're not in the same page as, say, for example, Los Alamos, where they're saying fairly, well, they'd probably say it's incremental as well, right, David? But bottom line is, write once, or just so you're saying that a little too restrictive, so you'd prefer to keep POSIX.
No,
Okay.
I really like that LANL is sticking their necks out and really just breaking all the POSIX semantics and keeping the API and seeing what happens. I wouldn't want to stick my neck out that way.
Okay.
But their success will embolden us to deploy this to 7,000 users. So I think that's a good approach.
Okay.
And just see what happens because most of our applications already don't rely on strict POSIX semantics.
Okay. There go your weekends, David. NERSC is waiting. Just easy. All right, very good. Thank you very much, Glenn.